the most exciting things about being a science teacher is being able to do really fun, exciting chemistry demonstrations for students, because it never fails to enthrall them. If you want some tips on how to do great, exciting chemistry experiments involving elements from the periodic table, keep watching. I'm here to meet Bob Worley from CLEEPS and Kay Stevenson from the Royal Society of Chemistry, who are going to show me how to do some of these demonstrations safely. Hiya, Kay. Hiya. What reactions have you got to show me then?
Thought we'd start with Group 1. What I've done is I've got the Group 1 elements out to have a look at. As you see them down the periodic table, so lithium, sodium, potassium, rubidium and cesium. And what I thought we'd do is just have a look at how easy they are to cut and then see what happens when they're exposed to the air, when we clean off the oil there. Lithium's actually quite hard to cut. And then if I just move that bit away, you can see the surface is quite shiny and it'll just gradually start to react and tarnish.
You can see it tarnishing already.
Yeah. Sodium's much easier to cut. It's almost like cutting cheddar cheese. It's that sort of consistency. And if I just cut a slice off there, and you'll see that that tarnishes much more quickly. You can see the surface is going. And the potassium's really easy and tarnishes almost immediately. If you just sort of move the oil off the surface, you can see that it tarnishes the bluey purple tarnish on the surface.
Now, you can't cut rubidium and cesium, can you?
No, rubidium and cesium are stored under argon in these sealed glass containers. And they just, you can see what the actual alkali metals look like when they've got no tarnish on them, very shiny, silvery metals. And cesium's quite interesting because it's got a low enough melting point that you can actually melt it from the heat of your hand.
The reactions of lithium, sodium and potassium in water are easily demonstrated in school as long as the CLEEPS guidelines are followed. Kay started with lithium.
And I'm just going to pop that into the water. I'll just dab off the oil off it. Okay, and then we'll just...
Next up was sodium.
This time we've had to take slightly more careful safety precautions. Got the big screen round the front and round the back, so this time we're protecting not just the pupils but ourselves as well. Okay, so let's have a go with sodium.
When sodium reacts with water, it produces so much heat that it melts the metal.
Let's have a go with potassium this time.
Okay.
Should be a bit more exciting.
Definitely more reactive. Rubidium and cesium are quite difficult to get hold of. They're not banned, but you should consult an organisation like CLEEPS before attempting them. Here's Bob Worley from CLEEPS with rubidium. He started by breaking the glass vial under oil.
This is the smallest amount going in first.
And here's a bigger piece. And as you'd expect, things get even more serious with cesium.
A small amount there, and I've got the glass, and that's the large amount, which will be the last one to go in.
And then he tried the bigger piece. Bob then showed me a very simple way of reacting sodium with a gas jar of chlorine.
I'm going to now heat the sodium directly. Now it's, there's the molten sodium. And here we go.
That's fantastic. It's very bright yellow.
Yeah, it was yellow flame test.
Exactly.
And also we're getting the smoke of the sodium chloride.
So that's what you're seeing that's white on the top?
That's right.
We then moved on to some group 2 reactions, starting with burning calcium in air.
What exactly are we going to be doing with this creme brulee torch?
Well, calcium requires a much higher temperature than a Bunsen flame to get it to work. And a creme brulee torch works really well.
Okay.
Now, to do this, I have to wear some protective gloves on my hand.
Lovely fetching orange?
They are lovely, yes. And here we go.
Do I have to step back at this point?
Yes.
Oh my gosh.
Bob then showed me how to reduce copper oxide using magnesium powder.
I've got here some copper oxide, 0.5 of a gram, and 0.5 of a gram of magnesium powder. And we can pass one to the other as quickly as possible like this to get a nice homogeneous mixture. We'll pour that into our bottle top. We'll place that on the pipe clay triangle. Again, we're going to have an intense white flash, and we do need to protect the pupils again, and we shall need to step back once to set it going.
Right.
The problem with this experiment is that you never quite know when the flash is going to occur, so you must never return to the actual experiment.
Whoa.
There we are.
My gosh, that was bright.
In group 6, sulfur has many reactions which can easily be demonstrated.
First one is reacting iron and sulphur. So what we've got in the bottom of the test tube is a mix of iron powder and sulphur, ratio of about 7:4. And all we have to do is heat it up and the two will react together.
Okay. Now, why do we have the wall there?
And this is just to stop the sulphur coming out and the sulphur fumes.
And, oh gosh, you can see it happen already.
It's a nice
Gorgeous
reaction to show the reaction of group 6.
And it happens really quickly as well.
Yeah.
Could students do this themselves?
Yeah, they can. You wouldn't want to do it on quite such a large scale if the pupils were doing it individually, but you can use a little mini test tube. Let's have a look at sulphur reacting with another element, this time zinc.
Right.
And what we've got in these two little weighing boats is 1 gram of zinc powder,
Right.
and 0.5 gram of sulphur powder, flowers of sulphur. And what we're going to do is mix them up,
Right.
and then we're going to heat them up. And then what we're going to do is put them into a little bottle top. We're going to use a bottle top as our little crucible rather than a porcelain crucible, because porcelain crucibles can crack.
Right.
The only thing you've got to remember is obviously bottle tops come with a plastic insert, so you have to burn that out before you use it.
Okay.
So we're just going to transfer the zinc and sulphur mix into the bottle top.
There we go.
Okay, and put them back on the... And we also need a screen to protect the pupils. Okay. And then we just need to heat up the zinc and the sulphur. And blue flame as usual, put it under, and then we can just take a step back and leave it to react.
Can I ask why we have to take a step back?
It can sometimes sort of spit out a little bit, which is why we've got the screen. Okay. And it should get going quite quickly, and if we just take a little step back. You see?
Oh, I can see what you mean.
So quite a nice vigorous reaction, but you can see where we need the safety screen.
Absolutely.
Yeah.
Finally, there's group 7, the halogens. I wanted to know which experiments I could demonstrate to show that the reactivity of the halogens decreases down the group. Of course, fluorine is out of the question for class demonstration. But here's Professor Holloway from Leicester University to show what happens when you direct fluorine at a hydrogen balloon. Fluorine is in a cylinder and comes out of the nozzle. Professor Holloway also set up the reaction between hydrogen and chlorine. The plastic bag contains equal volumes of hydrogen and chlorine, and all it needs is a flash from a camera. Next up is hydrogen with bromine. Bob prepared equal volumes of hydrogen and bromine in this gas jar.
Here we go. Fantastic.
Displacement reactions involving fluorine can't be demonstrated in class, so here's Professor Holloway again.
And on this paper we've got some potassium iodide, and we're going to let a little fluorine out onto the surface. And there you can see the iodine displaced. This time we have potassium bromide on the filter paper. This time we have potassium chloride.
Nothing appears to happen with potassium chloride because the liberated chlorine is too pale to see. Reacting the halogens with iron wool is an excellent way of showing that the reactivity of group 7 decreases down the group.
And what you're going to do is heat up the iron wool and drop it while it's hot into the gas jar of chlorine. And there you can see the iron wool's reacting with the chlorine. They're the brown fumes of the iron 3 chloride.
Fantastic. You can really see it reacting, can't you?
Yeah. And then you can see that the chlorine's disappeared, the green colour's gone out of the gas jar. Okay, this time what we're going to do is use some bromine to react with the iron wool. And we've put a few drops of bromine liquid, so I'm just going to warm up the bromine to get it to vaporise, and then heat the iron wool. And what we should see, once we can get the iron wool hot, is that it starts to react with the bromine vapour. At the moment all we've got coming out of the top is bromine fumes, and there you can see the glow and the reaction. All you're going to do this time is just warm the iodine up. It's a bit more difficult because it's a solid to start with. Just warm it up until you see the purple fumes, purple vapour. That's it. And let it go through the iron. That's it, just gently heating it.
And will the iron wool, are we expecting the iron wool to glow as well?
It'll glow, but it won't be as
Oh, you can see it happening now.
vigorous a reaction as with the bromine.
I hope you agree that the reactions we've shown are exciting. But please remember to practice the experiments and take the appropriate safety precautions.